Hi there, and welcome to another episode of the Wild Adventures of BIPN 105. My name's Ingmar, and I'll be your guide on this wild ride. My trusty Outback colleagues Mel, Callie, Chloe, and Jasmine will be joining us today. Crikey! Look at that! That's a nice looking frog if I do say so myself. Hey, have you ever wondered how frogs are able to jump so far? Well, every muscle has a neuromuscular junction, which connects the nervous system to the muscles of the leg and foot. Let's head back to the lab to look at this process with a little more depth. Well. We can see that my colleagues are working in the lab with a frog right now. Can you explain to the tour what we're looking at there, Mel?
In this lab, we examine the neuromuscular junction, often called the NMJ, of the sciatic nerve and gastrocnemius muscle of the frog. The sciatic nerve is made up of motor neurons that connect the nervous system to the muscles of the leg and foot. The neurons that innervate muscles are called motor neurons. In this lab, we look at A alpha motor neurons. However, there are other motor neurons that include A beta, A gamma, and A delta, but only A alpha motor neurons innervate skeletal muscles such as the gastrocnemius muscle. The NMJ is a chemical synapse formed by a motor neuron and muscle fiber. It allows for a motor neuron to transmit signals to a muscle fiber and create muscle contractions. Synaptic transmission at the NMJ begins with an action potential reaches the presynaptic terminal of a motor neuron. This causes a depolarization which activates and opens Volsch's calcium channels called PQ calcium channels. Calcium binds proteins on synaptic vesicles which contain the neurotransmitter acetylcholine. The vesicles are triggered to fuse with the cell membrane and release ACH into the synaptic cleft via exocytosis. ACH then diffuses across the synaptic cleft and binds to and activates nicotinic cholinergic receptor at the muscle end plate. The synaptic cleft is a narrow space between the pre- and postsynaptic terminals that is composed of basal lamina, a sponge-like structure filled with extracellular fluids so the ACH can diffuse across the cleft. Two ACH bind and activate each receptor, causing an increase in the end plate's permeability to sodium and potassium. Sodium enters and depolarizes the muscle fiber much faster than potassium leaves because it has a much higher driving force. The end plate potential is a graded potential based on the amount of ACH released from the presynaptic terminal, the amount of nicotinic cholinergic receptors activated, and how much sodium comes into the cell. If the end plate potential reaches threshold, a muscle action potential will fire. The signal is eventually terminated when ACH diffuses out of the synaptic cleft or is broken down into choline and acetate by the enzyme acetylcholinesterase. Choline can then be recycled by being shuttled back into the presynaptic terminal by a sodium choline cotransporter and converted back into ACH via acetylation by the enzyme choline acetyltransferase. The newly synthesized ACH is then transported into presynaptic vesicles by vesicle ACH transporters.
Wow. Thanks, Mel. That's intense. But it's really just the beginning. A muscle is composed of individual muscle fibers, which are innervated by just one motor neuron. However, one motor neuron can innervate many muscle fibers, so there's one NMJ per muscle fiber. When the stimulus is large enough to recruit all the muscle fibers, a maximum is reached. This is called the maximum MAP, or muscle action potential. In these studies, extracellular electrodes were used to record muscle action potentials. As the amplitude of the stimulus applied to the nerve was increased, both the CAP and MAP increased because more nerve fibers and more muscle fibers were being recruited. This continued until a maximum MAP was recorded, indicating that all A alpha muscle fibers had been recruited.
Created using Powtoon.